I want to welcome you to another statistical machine learning class. And those of you online, can you also confirm if you can hear me? I want somebody to confirm among those who are attending online if you hear me by talking.
We can hear you.
Thank you so much. And those of you at the back, can you hear me? Or everybody hear me? Okay. Once again, I want to welcome you to today's class. Of course, we started maths review uh, on Monday. And of course, I promise we're going to continue from where we stopped then today. Okay, so I quickly want to go to what we have achieved and what are left to be done. I've walked you through the vectors and matrices. We've done matrix decomposition, but where we're going to start from today is random vectors. Then we're also going to talk about univariate optimization. Okay, so I'm quickly gonna go into uh the random variable that I mentioned. Just give me 1 second. Okay, let's start from here. Mean and variance, okay, of a random variable x. We want to reveal from statistical perspective because this course is about statistical machine learning. Of course, the word statistical is just for us to gain from from transparency in statistics that we have in statistics. If I have a random variable x, okay, we may be interested in summarizing that. Summarizing that is to provide some basic statistical summary, like the average. Okay. Now the question is, we need to put into consideration the nature of the random variable. I know before now, before you were qualified to take this class, or you've already taken some theory of it, to a certain level of the theory of statistics. So we are revisiting that because their idea is going to be in use in statistical machine learning. So if I want to figure out the expected value of S, the very first thing that what I need to know is whether S is discrete, whether the variable under investigation is discrete or is continuous. If it is continuous and I want to figure out the expected value of S, then I need to be able to understand what the probability density function of that random variable is. So right now, if I want to find the expectation of S, okay, if S is continuous, then I'm going to do integral, okay, then S, then I'm actually going to perform that operation. I remember we did uh, in another way. If I wanted to write that, this is exactly what I mean. Integral S f of S, ds. The f of S is a probability density function of that particular random variable. Okay. So this is when, your S is continuous. If it is discrete, instead of us using integral sign, it's going to be a summation sign. Okay. This is just to have a recap on the theory of statistics that you've done before. If you have a random variable S, okay, and you want to figure out the expectation of S, which is the mean, you need to be able to know whether you are working with a discrete or you're working with continuous. Now, whenever mean is involved, okay, variance is also going to be involved. How do I find variance? Okay, what is variance? Of course, we know that's a measure. We actually uh, want to measure how uh, you know, the the data actually spread out. Okay, we're going to obtain the variance of S by using this formula that I can also rewrite as expectation of S squared, okay, which is the second moment minus expectation of S, okay, or squared, okay? So whenever mean is involved, variance is going to be involved. And let me also, a situation where we got more than one variable, okay? Uh, we may also we may be interested in the covariance as well. Okay, the covariance measures how variables, varies together. Okay, and if I actually a situation where um, the variables are in different scale, and we don't want a situation where a particular variable will dominate the other variable. Because if I'm working with mass, for instance, MASS, if I'm working in gram, I find the covariance. If I change to kilogram and I find the covariance is not going to be consistent. I'm actually going to have different values when I change the units of the variable under investigation. And that's why we need correlation. Then we need to standardize our covariance so that, and that's why correlation is unitless, doesn't have units, okay? Because we've been able to standardize, the covariance. So if I want to know, in addition to understanding the nature of the relationship between two variables, if I want to know the strength of the relationship, whether it is weak or it is strong or it is perfect, then I need correlation. The covariance cannot answer a question that has to do with the strength of the relationship. Covariance is only going to tell us direction, but why correlation tell us both direction and the strength of the relationship. Okay, I also want you to know this situation where a covariance is zero or correlation is zero, then we're going to say the two variables are independent. Otherwise, they are not independent. So I just wanted to take note of that. Okay. Now, we have some kind of properties. Okay. What if I'm working with a linear combination where A is a constant? Expected value of AS, where A is a constant, is actually A multiplied by expected value of S. If I'm talking about the variance of AS where A is a constant, then the constant is going to become a squared. That's why you have a square variance of S. For instance, you got variance of 6x. Okay, I'm actually going to say this to be c squared of variance of x, which is going to be 36 variance of s. Okay, and we also have a situation where I got two variables, two different variables, x1 and x2, and each of them has, you know, uh, a kind of coefficient, the form of which is constant. The x1 has a constant, and B and S2 has a B as a constant. And I want to look into the covariance between two different linear combination. We can look into the covariance between two variables, x1 and x2. We can also look into the covariation between two different linear combination. Okay, so this is going to be multiplying the constants in each linear combination. Then I'm actually going to multiply that by the covariance x1, x2. So we're just trying to let you know about this relationship. Okay, from there, I'm actually going to move I want to go to so many variables. I just walk you through when you have a single variable. Then I'm actually going to call a univariate when you have a measurement on one variable, one at a time. That's called univariate. Okay. I may want to perform some basic statistical measure. Maybe I want to find the mean, I want to find. But what if in a situation where I got more than one variable? Okay. If I got more than one variable, I can use the idea of a vector that we have learned in this class from linear algebra. Okay. Take a look at this guy now. Give me 1 second. If you take a look at this guy now, what this guy is telling me now is I have p numbers of features, p numbers of variables. I'm representing that using a vector right now. And do you know that if I have a vector, and what constitutes this vector, s1, s2 up to xn, each of them a random variable, then I want to obtain the mean of each of that. Then I'm going to end up getting a mean vector. Take a look at this. This now become a mean vector because I'm seeking to get the expectation of each variable. Expected value of x1 will give me the mean one. Expected value of x2 will give me the mean two. Expected value of x3 will give me the mean three, and so on like that. So I'm actually going to have a mean vector. Okay. And let me tell you this. Each of these variable may be discrete, may be continuous. Okay. So, and I told you the other time when we're dealing with the univariate, where we're only focusing on one measurement at a time, we can find the mean. The only thing we can do when we have just one variable is to find the variation, to find the variance. But the moment you have more than one variable, then we need both the variances and the covariances. And that is why we actually need a covariance structure. Take a look at this guy now. This is a covariance structure. So if I have if I have an X where that contain P numbers of variables, and if this is the mean, then I want to find the variance of S, and this particular S is actually multivariate. Okay. Now, the formula for my covariance is going to change. Okay. You remember the other time when I was dealing with two variables at a time. I'm only going to consider x1 and x2, but right now I'm gonna go into a transpose. Look at that. Expected value into x minus expected value of s, then another one with a transpose. And that is actually going to lead us, that's going to lead us to what we have now. Now I need you to pay attention to what I have now. This guy is the variance of x, where x as x1, x2 up to xp, p numbers of variables. Now, this is what we call the covariance matrix, where in the diagonal, you're actually going to have the variance of each variable. In the off diagonal, you're going to have the covariances. Now, if you take a look at this now, oh my God, this is the covariance of x1, x2, the covariance of S1, S3, and so on until you get to X1, SP. But let me tell you this, the covariance of X1, S2 is the same as covariance of S2, S1. And that is why if you take a look at this is going to be a symmetric. Okay. So this is the covariance matrix, and it's going to be a square matrix, P by P. It's going to be P by P. Okay. I just walk you through all of these. Okay. Now that is the covariance matrix. Covariance matrix is very useful in statistical machine learning, particularly when by the time we start principal component analysis, the input matrix in principal component analysis is covariance matrix. Not only that, we use it as input in factor analysis. Okay, we use covariance matrix a lot. Okay, within statistical framework and machine learning algorithm. Okay, now The same thing that we did the other time when we were working with scalar. I can also figure out the mean of a linear combination for multivariate. I can also figure out the variance of a linear combination for multivariate. Oh, I'm gonna quickly walk you back. I'm gonna walk you back a little bit. I needed to pay attention to this. Okay, this applies to when I'm only focusing on one variable. Okay, at a time, S is not a matrix. I only have just one variable. Okay, and this applies to when I have two variables. Okay, but what if in a situation where my S is a matrix, it has so many variables? How do I perform the mean of a linear combination? And how do I find the variance of a linear combination? Take a look at this. In that case, this particular A is going to be a constant matrix. Okay. Now this S is actually going to be a vector that has x1 up to xp. Okay, so finding the expectation of that is going to be I'm only going to do that matrix multiply by the vector mean. If I want to find the variance of AS, don't forget the other time when I was dealing with a scalar, and when I was dealing with a univariate where I have a lowercase a x, okay, I remember I said there's going to be a squared, okay, of variance of x, right? But right now, because this guy, okay, because A is a matrix, this guy is a vector, instead of me to write A squared, I'm actually going to write A transpose. Okay, I put A at this end, I put A transpose at the right hand side, then I'm going to put the variance of S in the middle. But let me tell you this, the variance of S, you are putting in the middle now. Okay, this particular variance of S you're putting in the middle is actually this guy here. It's actually the whole of this guy here. Don't forget, that is the variance of S. Can you see that? So they are going to be matrix. Okay, so that's that. Now, is there any question on on this review of statistical aspect of this? Is there any question, whether in person or online? Like I said, feel free to ask me question in case you don't get the information. I'm here to do clarification. Okay. Now let's now move. We want to move right now. Okay. I want to welcome you to univariate optimization. I want you to pay attention to univariate. I only want to consider one measurement at a time. One measurement at a time. Okay. Now, suppose we have a function. Okay. That's a function of that x that I'm talking about in such a way that we actually doing some mapping. Okay, we're mapping from S to f of S, and we're mapping from real number to real number. Okay, X values in the real number, f of S also values in the real number. I'm mapping from input to output. Okay, but I'm mapping from real number to real number. Okay, I have a particular function of S, but I told you from day one. Okay, we have ambition, we have intention. What if we are seeking? What would be the values of S? Maybe our intention is what is the values of S that can minimize a function of S? Okay, I'm going to say that again. If you take a look at this, I'm actually looking for the values of S, the optimal values of S that will enable me to minimize a function. Okay, now I'm seeking to get this guy. I want to get the minimum f of s. And you know what this guy mean? This guy mean that value of s that give me the minimum function value. The values of s that I'm actually going to plug in into a function that can give me the minimum ever. Okay, with that, This is an optimization process. The optimization means, optimization is about minimizing a function or maximizing a function. Okay, but right now, I want to walk us through the minimization aspect of a function. We do that a lot using statistical machine learning algorithm. Now, let me tell you this: to minimize a function from what you've done in calculus, okay, we're actually going to ensure first that function is differentiable. You can perform derivative up to certain order. Okay. Now, what calculus tell you is, how am I going to know at the end of the day if we have succeeded in optimizing a function? How are we going to guarantee that we have minimized a function? What I'm going to do is, if we perform an antiderivative, okay, and we plug in the particular value we believe is going to do the job, the particular value we believe is going to do the job is x star, okay? When we plug it into the derivative, when you see f prime, that's a derivative of that function. Then if that equal to 0, then we're actually going to say that may be optimal value in a way, okay? But that is not a sufficient condition, okay? That may be necessary, but I'm still going to walk you through sufficient condition, for that. So for instance, if I actually give you this, okay, I have a quadratic function, okay, and I wanted to minimize that, okay. So all what you're going to do is you differentiate that, right? When you differentiate that, what are you going to have? I think I'm having 2x, right? Plus 8, right? So this guy is actually f prime of s. Then I equate the derivative to 0, right? Okay. When I equate that to 0, I solve for x, okay? This is going to be 2s equal to -8, right? And of course, I'm actually going to say s equal to -4. Okay. We call that a stationary point. Okay. And another thing we do in calculus is, okay, if I really want to know whether this is going to minimize the function, I can do second derivative. When the second derivative is greater than 0, then I'm going to say, oh, it will minimize. Okay. So now when I do the second derivative here, take a look at this. When I differentiate that again, f prime prime of x, automatically that's going to give me 2, right? And because 2 is greater than 0, I'm actually going to say the particular value here minimize is actually going to minimize. That's what you do. That's what you do in calculus. Okay? But what if in a situation where we may not be able to solve the equation analytically like this, that we need to resolve into numerical means? I need to pay attention to this guy. If you take a look at this example here, look at this one. Oh my God, that would be difficult to navigate. You have exponential s, to power, s minus log s. If you want to minimize that, if you differentiate and you try to do what I do the other time on the polynomial function, that is never going to have an open result. You have to resolve into using algorithm, you have to resolve it. What I mean is, you resolve that cannot be solved analytically the way I quickly solve this. Okay, we have different kind of functions that you may be giving, and that is where we need algorithm. Okay, what algorithm is going to do, we're going to use an algorithm that can generate the results. So which means it will involve iterations. Has anybody heard about iterations? Where it's going to be iterating and finally it's going to converge to a particular value. That's a numerical analysis. So situation where analytical, intervention may not work, we resolve into numerical approach. We have different numerical method that we use in mathematics. If you want to talk about method of Newton-Raphson, has anybody heard about Newton-Raphson? Okay, we got so many numerical approach. Okay, now I quickly want to move right now to something else. Now I just give you a background to that. Now, okay, now look at what I said. I said sometimes directly solving the equation is not feasible. You know, the polynomial that I quickly solve, that is feasible. But it depends on the complexity in the model structure. Okay. So what do we do then? And also I say we need to resort to more general iterative algorithm. Okay, the good news, we're gonna solve it to general iterative algorithm. And how does it work? Okay, don't forget the other time when using the knowledge of calculus, we actually said the derivative, of that particular stationary value has to be have to be equal to zero, right? Now I said if the derivative of the function is less than zero, that is negative. Okay, if and only if, let's say the reason why this guy is less than zero, please pay attention. The reason why this less than zero, if it is because f is decreasing at s, if this function of s output is decreasing at the input, okay, and maybe the reason why this guy is greater than zero is because f of s is increasing at s. Because what we actually want, what we want is for us to have what calculus tell us is that f prime of s has to be equal to zero. When it is less than zero, that's an issue, right? When it is greater than zero, that's an issue. But you need to first identify the reason why the derivative is less than zero and why it is greater than zero. So if it is less than zero because of the fact, if the derivative of the function is less than zero, because of the fact that your original function is decreasing, okay, at s, or it is greater than zero because the original function is increasing at s, then what do we need to do? Now, depending on what you see, please pay attention. If this is what you notice, if this is what you notice, your function, okay, the derivative of the function is actually less than zero because of the fact that the original function is decreasing at s. The intervention may be to increase. That's what I say here. Look at that. That would be the intervention. The intervention would be, okay, what we're going to do, let's increase s then, okay, so that we can make the function smaller, okay? So that's what I mean. But what if in a situation where what happened is actually this, okay? What if in a situation where what happened is because of this? Maybe the first derivative is greater than zero because the original function is increasing at s. Okay, increasing at s. Then we decrease the s. Look at that. That would be the intervention. Can you see that? Okay, we have to decrease the s. Okay, now you can see that one is talking about increasing, the other one is talking about decreasing, depending on what you observe. Okay, therefore, what we're now going to do to move to the next position, we're now going to have an iterative equation. Take a look at this, where we're going to have the new values for x. That's why I call s new equal x. That the other s is the old value of s because I want to update. Old value of s minus t, that very t, I'm going to choose that. You're going to choose that. But it has to be positive. It has to be greater than zero. Okay, then f prime of s. So what we're now going to do, the next steps are determine how much to increase or decrease. Okay, and I said what to determine t. So you have to use your discretion to decide on T value. But this is what happened. I'm going to show you what we use generally. Okay. And I said the naive approach is to start for some number T to be equal to 1. Okay. So when T equal to 1, okay, if I come here, I plug in T to be 1. Then I'm trying to say S new equal to X minus the derivative. That's what I mean. Now, how do I know I have a good result? Take a look at this. So whenever whenever I got my X new and I plug the value of the updated S new into a function, if it is less, if the value that I got is less than the original old function, then that is good. Does that make sense? Okay. Now, because our intention is to decrease, okay, we want the fx new to be less than the old function. Okay. So, but situation where it is not all the time that your updated value is going to be a good one. We don't, you could overshoot. We don't want overshooting. Overshooting, take a look at this. If I have in a situation where, take a look at this, where your fs new is now greater, that's not good. We want it to be smaller than the original function, and that's too bad. That means you are overshooting. Okay. Now, whenever you have this, you see that you are overshooting, then you have to consider a smaller value of t. Don't forget, naive approach is to start your t from 1. And that was what I said. I said, so let's try a smaller step size by shrink t by half. Can use 1/2. Okay. Then you now keep doing until you find a suitable one that will actualize your objective of decreasing the function. Okay. Don't forget, when you are minimizing, when your goal is minimization, you are looking for the values of input that will decrease the function, that will minimize the function. Okay, if that is taken, we're going to move right now. Okay, I think I just discussed that. Okay, I just discussed that. Now, the K that you are seeing here, okay, so one of the algorithm that we use is what we call gradient descent algorithm. Okay, and if we want to begin, we're going to start with initial value. In iteration, we start with initial value. It's not just, it has to be a very good initial value because we want a situation, or we don't want a situation where our algorithm will get stuck. Okay. And K that you see here is just the number of time it converges, the number of time, the number of iterations before converging to a result. We don't want our iteration to take longer. We want it very fast. Okay. So that is what I'm actually discussing here. Okay. You want iterate, you continue to iterate until the function value become very stable. When it becomes stable, that means it has converged. Okay. Now, I need you to pay attention to this. In calculus, if where you are able to guarantee this, if you're able to guarantee this, that is not sufficient enough to say that the value you are, I mean, that may not be a minimum value. There's something that we call local minimum. There's something that we call global minimum. We always want to go for global minimum. We don't want a minimum value within the domain, within a particular environment of the domain. We want it to be minimum ever, putting into consideration the entire domain of the inputs. Okay? So, unfortunately, even if you achieve this, it's not enough to say that you've been able to find an optimal value. Does that make sense? And so I just wanted to get that information. Okay, that will now take me to local minimum and global minimum. Let me tell you this. Whenever We are looking for minimum of a function. Has anybody heard about piecewise polynomial in high school? Piecewise. Okay. When you have a piecewise polynomial, it's going to say, okay, this function exists given this interval. This function exists given this interval. We don't want our minimum to be local. We want it to be global. I remember what I used to tell my daughter that is into track. She's into 100 meter. And I say, oh, thank you. We appreciate the fact that you record the best time for in Minnesota in 2025 for high school girls, but that is Minnesota. I wanted to go to New Balance in Pennsylvania, Philadelphia, compete with other athletes at nationals in at national level, and record the minimum time in 100 meter. That would be global minimum. Okay, we don't want a local minimum. We want a global minimum. We don't want a situation where within the domain affairs, you only achieve, your function, your algorithm gets stuck in a local minimum. Okay, and I'm going to discuss with you as time goes on, what can we do, or what do we expect the nature of the function to be before algorithm can escape being get stuck in local minimum. What do we mean by it's not because of that? I want to walk you through local minimum. Now, let's say there exists, let's say we have a row. Please pay attention. I want to be explaining each notation. We are now working with symbols now. Well, the reason why at times, statistics or machine learning algorithm may not be friendly is because of the fact that our students don't really understand what notation represent. Let's start with a row greater than zero. Let's say this row is a distance between a particular value that I settle for. I settle for a star. I settle for this. Maybe we settle for this to be minimum. Now, this particular star is around a particular neighborhood, and the distance between that very star and some other values within the neighborhood is actually what we call rho. And that's why I said that absolute value of the difference is less or equal to rho. Okay, so what we're trying to talk about, if I plug in into the function and I achieve this, okay, I achieve the fact that the new function with the optimal variable that I settle for is less or equal to the old function. Only if this happen, that's a local minimum. We don't want a local minimum. Local minimum is a problem to us in the machine learning world. Okay. Now, we want a global minimum in such a way that in all neighborhood, not only within a particular territory, okay, and that's what I said, a global minimum is a true optimal value for all feasible point, okay? And when you get a local minimum may not necessarily be a global minimum. Does that make sense? Now, I was telling my daughter that okay, if you want, you can achieve global minimum even in Minnesota. If your time in Minnesota is the best time ever nationally, then in that situation, local minimum translate to global minimum. Okay, because they make use of time. Okay, so we have situation where local minimum may be, but local minimum is not global minimum. So what we normally want is global minimum. I'm going to show you a picture that depicts that. Take a look at that. Okay, that means if you have a local minimum, which is actually here, which is actually which is actually here, then for local minimum to be the same as global minimum, then that should be minimum ever. But situation where you have a look at this. This is another minimum. This is minimum. This is very smaller than this. We don't want something like this. We want something like this. This is what we want. And if you're seeking maximization, we don't want local maximum. Okay, we want global maximum. Does that make sense? Please pay attention to that. And that was why I said in general, okay, the fact that the derivative of your function equal to zero, okay, is not sufficient to guarantee an optimal value because the value that you may settle for may not be global. Okay, so that's what I just wanted to know. I'm moving. Now, how? Oh my God, statistical machine learning is like a story because this is what we are starting next week. Statistical machine learning is like a story. Now, the question is, if I want to get a global minimum, I don't want my algorithm to get stuck in local minimum, then what do I expect the nature of my function to be? My function should be converse. That is why we're going to conversity now. Okay? I want a situation where I don't want my algorithm to get stuck in local minimum. If I want to guarantee global minimum, then the nature of my function has to be converse. Now, I want to walk you through what do we mean by converse function. Okay, now I need you to pay attention. Okay, uh, if I take any 2 points in the domain, okay, any two values, x and y, in the domain, okay, now when I take the 2 point, okay, if you take a look at this, t is a weight, okay, which is going to be from 0 to 1, which, okay, now if you take a look at this guy, please pay attention. Uh, let me clean up. I take 2 point, okay, within the function, and look at this guy inside. This particular guy is a point, okay, between x and y. Okay, why are we having t and 1 minus x? Like taking percentage from this and percentage from that. It's like a point between x and y. If I have a point between x and y, okay, and we have to ensure a function is going to be a converse is if that function lie below, you can see this guy lie below this chord, lie below this straight line. Mathematical way of saying that is that if I put that point into a function, it should be less or equal to that. It means the line that you draw between the 2 point, okay, in the function must actually, that line must lie above the function, which means the function should be below that line. That's what we mean by converse function. Okay, converse function guarantee, uh, global minimum. Now, I want to walk you through, and that's what I said. But what if in a situation whereby it doesn't lie, the function lie above the line, then it is concave. If something is below, I want to switch it to be above. I will multiply by -1. Does that make sense? So when f is a converse function, okay, when f is converse, if I multiply that function by negative, it become a concave. Now, if I want to talk about the equation for the concave, okay, since it's the opposite, the inequality here, okay, the inequality here for concave is going to change to greater than sign. Does that make sense? It's going to change to greater than sign. Now, you know what I want to walk you through, what I want to show you now. Okay, what I want to show you now, what are the examples of converse functions that we have? When you are working with exponential, working with the power functions, working with the logarithm, working with let me see, logarithm of s. I'm thinking whether that's, logarithm on, I think I'm going to check that when you sketch the logarithm. Okay, I'm going to check whether that should be a negative for log s. So now these are example of a converse functions. What if I give you an exam? Investigate whether a particular function is converse or not. That's what we're going to be doing next week. Okay, but these are examples that I have on ground. Okay, now the help of convexity. If I want to minimize a function, okay, Conversely, we ensure that our algorithm do not get stuck in local minimum when we are seeking optimization goal or minimization goal. And let me tell you this. Uh, Here I said we want to solve the problem, minimize f of s. Okay. Whenever we want to minimize, there's always going to be something like a constraint, maybe subject to certain constraint. Okay. So if it is subject to a constraint, we're going to call that constraint optimization. If there is no any constraint, you only have objective function, then we're going to call that unconstrained optimization. So I just wanted to know that. I said such a problem is called unconstrained optimization problem because we do not have extra constraint on S, except that the f of S should be well defined. But situation where you have a constraint where it is subject, it means you have additional restriction, that will be called a constraint polynomial. Okay, so I said when f is differentiable and converse, you can now see f may be differentiable and not converse. If f is differentiable, you can see have a stationary point, but it may not be optimal point. Okay, so it has to be converse, and if the moment it is converse, it can guarantee global minimum. And of course, for unconstrained converse, we can obtain the solution, with that. I think okay. If we can try this. Do you know in statistics, some of you may be wondering, how do we get the formula for finding mean? It was through optimization. If I optimize, this is a quadratic function, and this has been proved to be a converse function. If I differentiate with respect to mu, let's take a look at that. If I do the derivative of f mu, okay, with respect to mu, okay. Now I want to differentiate that. I'm actually going to have two, okay. When I have two, summation, okay, mu minus si, right? Then I say equal to 0. When I say equal to 0 divided by 2, I'm only going to have summation into mu minus si, right, equal to 0. Okay, don't forget our I start from 1 to n, right? Okay, mu is a parameter, it's a constant. When I multiply this by that, it's going to be n mu. That summation, when it's multiplied by a constant, become that minus summation times s. Oh my God, that becomes summation I, which is equal to 0. When this guy equal to 0 now, what am I going to have? This is going to become n mu. N mu equal to what? N mu equals summation si. Okay, now I want to find mu. Okay, don't forget, I want to find the optimal mu, which is going to be summation s divided by n, which is going to be the sample mean. And that's how we know sample mean, we got sample mean to be an optimal value for the population mean, through optimization. This is where I'm going to stop today. Okay, we're going to continue, from the material uh on Monday. Let me even see what do we have. 1 second. Let me see what do we have. Oh, okay. I think I was just explaining. Oh, then move to multivariate. Okay. And that's all. Okay. All this one easy. Okay. So that's all I got. Uh, See you on Friday. I was thinking today is Friday. Today is Wednesday, right? Is it Wednesday? Oh, Friday. See you on Monday. I'm happy. I'm gonna relax. Yep. Enjoy your weekend. Bye for now.